Hi guys, sound check. Since there are only 4 of us, I suggest to wait like 1 minute. So we will start in 1 minute. I've heard that you have some unpleasant deadlines today.
Well, probably not today. We had a really annoying deadline yesterday. It was our programming project, and it's actually was really large, but we had an opportunity to postpone the deadline up to tomorrow.
Yeah, that was my decision, as you may guess.
Yeah.
Because I'm the only one.
Thank you so much.
Here.
You saved our souls.
I hope it will be enough. Is it enough? 1 additional day?
Yes, probably it's enough. Thank you very much.
Okay, no problem. Because yeah, there are some collisions during the process, so it's very convenient to have such an opportunity. You know, I was a student, as you might guess. So, okay. I see that there are 11 of us. Probably we may start. Okay. So we want. So I want to discuss everything that was during the lecture, and I want to start with some technical things like computing generators for some ZN star and so on and so on. So let me recall the main result. So if we are given some natural n, and let's factorize it into prime factors, then Zn star is isomorphic to Zp1 k star times Zpr kr star. So that was the first claim. This is another version of the Chinese remainder theorem. And this is an isomorphism, so it goes like this. So if you take an element A here, you just map it diagonally, which means that here you take A modular P1 to the K1 and so on, and here A modular PR to the KR. So the map is exactly the same as in the Chinese remainder theorem. The only difference here that you don't take all possible reminders here, you just take all the reminders which are co-prime with n. And the same is on the right-hand side. And this is also is an isomorphism. And if you want to produce the reverse map for this isomorphism, you apply exactly the same method we used in the original Chinese remainder theorem. So if you want to apply it to several factors, so you usually do it like this. So for example, Zn star, first of all, you have this map Zp1 K1 star times Z, and here, let me write it like that, P2 K2 and so on, PR KR star. So you make one step, and for this one step, you know the way to produce the inverse map. Then you make the second step, Zp1 K1 star times, and you split the second factor, which is Zp2 K2 times Z, all the other primes here. So, and this is isomorphic to this. So, and you know how to produce effectively an isomorphism from this guy to this one, and you just apply the identity map to this factor, and then you compose this into one resulting map, and this is how you compute a map in the opposite direction. Do you have any questions regarding this? Okay, so let's try to compute some generators for prime numbers. So let's discuss this first example, Z5 star. So what are the elements of the Z5 star? First of all, the elements of the Z5 are 0, 1, 2, 3, and 4. So Z5 star consists of all the elements co-prime with 5, and here we just need to exclude the first element, which is 0, and all other elements are co-prime with 5. So let's try to find all the generators of this group. So the general result says that you may find an isomorphism with Z4. Well, here your prime number pi is 5. It's odd, so this guy must be cyclic. And what is the order of the cyclic group? Well, the order of the cyclic group is the amount of elements here, which is 4. And by the general formula, it's pi minus 1. Well, you must multiply it by pi, p to the k minus 1, but k is 1 here. So this is the only factor. So this is the order of the element. So how do we find all the generators? Could you find the generators of this group? By the way, is it clear what does it mean that I want you to find the generators? Is it clear what the generator is here?
An element that forms a subgroup?
Well, not just a subgroup. We want to find all the reminders here such that its cyclic subgroup is equal to the whole group. That's the definition of the generator. It generates the whole group. But what does it mean exactly here? It means that each element of the Z5 star is presented in the form like this. So all the elements of Z5 star are presented as powers of your element A. So how do you, could you find the generators here?
Is it 1 and 4?
Let's check. 1 doesn't work. Why?
Because it's neutral element.
Yeah, and if we take 1, what is its cyclic subgroup? Its cyclic subgroup consists of 1 only. Yeah.
We have multiplication, sorry. Yeah.
Yeah, we have multiplication. Yeah. When you see the star sign, we have multiplication. So let's compute all the powers of 2, for example. Let's start with the element 2. Well, how would I check the subgroups? Let's take an arbitrary element 2. And let's start rising to powers. So first of all, we have 2. The second power is 2 to the 2, which is what?
4.
Which is 4. So 2 goes to 4. Okay. Now, 2 to the 3 is 4 times 2, which is 8. But 8 modular 5 is 3, which means that the next power is 3. And since raising to a power must go through all the elements in cycle, well, the next option is obvious. 3 must go into 1, but let's check this. So 2 to the 4 is what? Is 4 times 4, which is 16, and modular 5 is 1. So we see that the next power is 1, and then we go like that. So we see that each element of the Z5 star is a power of 2. So the subgroup generated by 2 is the whole Z5 star. Now, what if I take 3? Oleg, that's not true.
Oh, 3 will be the same because 3 is the inverse of 2?
Yep, that's right. That's precisely the thing I want you to notice, that 2 times 3 is 6, which is 1 modular 5, which means that 3 is 2 inverse, but 2 element and its inverse generate exactly the same group. So 3 generates Z5 star. And what about 4?
Four and 1, because 4 multiplied by 4 is 1.
Yep. Is this. Because when you rise 4 to the second power, you get 1 immediately. So 1 and 4 generate a subgroup. So this is an explicit computation. Do you have any questions regarding this brute force method? Okay, now let me show you one interesting trick. So suppose we did this computation, like we passed through here. So we may skip the step 1 because it's always obvious that 1 generates on the trivial subgroup, but suppose we found a generator. That was like, we were very lucky. Our first non-trivial attempt found
what's the inverse element of 4 then?
The inverse element of 4, it's 4. Because 4 times 4 is 1. 4 is inverse to itself.
I always forget. Yeah, multiplication. Okay.
Yeah. 4 minus 1 equals 4. So now, suppose, because well, for me, it's very natural when I see the star symbol here, I use multiplication. When there is no star here, I use addition. But yeah, you have to get used to that. But I'll promise it's not that hard. So suppose now we found a generator. What does it mean exactly? Well, it means that we found this map, this isomorphism between Z4 and our group, which takes each element k to the kth power of a. And isomorphism means that your groups are exactly the same. And this map is just a map which renames your elements. Let's look how the renaming map works. Like here you have 0, 1, 2, and 3. and here you have 1, 2, 3, and 4. Yep. So where does 0 go? So the element 0 goes to the element 1, because you raise, well, here, yeah, I forgot to say, here your A is the element 2. So each element here is presented uniquely as a power of 2. So, and we have already computed all the powers here. So the element 1 goes to the first power of 2, which is 2. Oops, I wrote the wrong symbol. So then we have 2 and 3. So then the element 2 goes to 4, because the second power of 2 is 4, and the element 3 goes actually to 3. Oops, wrong color. So you see that you have a bijection between all of those elements and these elements. And the operation here is addition, and the operation here is multiplication. So if you add these two numbers, what will you get? You will get 3. It's obvious here on the right-hand side. But this means that if you multiply these two elements, you also get 3. And indeed, if you multiply 2 by 4, you will get 8, which is 5 modulo of, which is 3 modulo of 5, and the result is 3. So, I mean, so this group and this group are exactly the same, but it's easier to deal with the right-hand side, because here the operation is easier. So it's easy. So if we know the right-hand side, it's easier to compute everything. But then we use this translation to this bijection to translate every property of this group to the property of this one. So is it clear by now what's going on, or should I explain at least something? Okay, but now if I want to find all the generators here, it's similar to finding all the generators here. So, but how do you find a generator here in Z4? So now it's a question how to find a generator in Z4. Well, in general, when you want to find a generator in Zm, so a number A in Zm is a generator.
GCD and M is 1.
What again?
Something like GCD of A and M is 1, something like that.
I can't hear you. Could you repeat your?
Maybe something like GCD of A and M is 1 or something like that.
Yeah, yeah. A and M must be coprime, which again means that A belongs to Zm star. But how do you compute? But here it means that in case of Z4, the generators are the elements of this set coprime with 4, and it's clear how to find them. 1 and 3 are the elements coprime with 4. It's clear here. And 0 and 2 are not coprime with 4. So it means that these elements are marked as the generators. So via our isomorphism, we get that these elements are the generators, and these are all generators here.
Okay.
So is it clear what's going on now?
Yes.
Do you have any questions? Okay, so, and now also it's clear that the element 2 generates here a subgroup of 2 elements, 0 and 2, which means that the corresponding elements on the right-hand side, which is 1 and 4, generate the subgroup of two elements. So here, the element 2 generate this subgroup. So here, the element 4 generate the corresponding subgroup. And this is how you use the isomorphism. So it's very easy to compute everything on the right-hand side, and it's very complicated to compute everything on the left-hand side. So if you have this isomorphism, for example, you have already found at least one generator. In order to compute all other possible generators, you may use this isomorphism. You don't have to do everything by the brute force method. So since you already know at least one generator, you may switch to the right-hand side and compute everything here. And then translate all the results to the left-hand side. Okay? Well, let's try to compute some generators for another group. Let's try Z17 star, which is, since 17 is a prime number, is Z16. I want to show you some additional piece of information. So what are the elements of Z17? These are the numbers from 1 to 16. So if well, it's unpleasant to write all of them, but we still are able to do that. So these are all the elements of this group. So now we know that the element 1 is not a generator, so we may exclude it. But what if we want to compute a generator? How do we start? Well, first, let's take randomly any number. So the best choice is just the first possible number we have, the smallest possible, which is 2. Let's try to raise it to a power. So 2 squared give us 4. If we multiply 4 by 2, we get 8. If we multiply 8 by 2, we will get 16. And actually, 16 is the same thing as -1. Now, if we multiply 16 by 2, is the same thing as -2. And -2 is the same thing as 17 minus 2, which is 15. So we will get 15, which is -2. Now, if we multiply it by 2, we will get -4, which is 13. So it's -4. If we multiply it again by 2, we will get -8, which is 9. And if we multiply -8 by 2, we will get -16. But since 16 is -1, we will get 1. And we see that 2 is not a generator. It generates a proper subgroup. Here is the list of all the elements in this subgroup. We just cycled through all the elements in the subgroup. So 2 is not a generator. So here I demonstrated a way to compute the powers using this simple remark, that you don't need to use the original name of the element, like 16, because it's hard to multiply 16 by 2. Well, we know that the result will be 32, but 32 model 17 is 15. But how to see this quickly? Well, in order to do that, you just present 16 as a -1, and then 2 times 16 is -2, and -2 is easily computed by this observation. So, do you have any questions by now?
No.
Okay, so, but now I claim that all other elements are actually generators. How do we know that? Well, let's take we know that our group, Z17 star, must be Z16. But how many generators are there in Z16? Well, this is the same. So what is Z16? It's the set of all reminders modular 16 from 0 to 15. And what are the generators here? The generators here are the numbers co-prime with 16, but these are odd numbers. So how many odd numbers are there? Exactly the half of all numbers. So 8 even, and 8 odd numbers. And all odd numbers are co-prime with 16, so they are the generators. So now let me see how many numbers are marked here. 1, 2, 3, 4, 5, 6, 7, 8. And how many are left? 1, 2, 3, 4, 5, 6, 7, 8. So exactly 8 numbers are left. And we know that there must be 8 generators. So all of these are actually generators. So we didn't even try to compute the powers of the element, of all the elements like 3, 5, 6, and 7. But we know by this computation that these are the generators. So do you have any questions regarding this computation? Is it clear to everyone?
Yeah.
Okay.
Could you explain one more time how we decided that all the left elements are generators?
Well, all the elements marked by the blue color are not the generators because they belong to a subgroup generated by the element 2. So if we take, so we computed that if we take the subgroup generated by the element 2, it's not the whole group. So everything which is inside this subgroup cannot be a generator because it generates something which is not greater than this subgroup. So the generators must be outside of this subgroup. So everything that is marked by blue is not a generator. That's the first claim. But so the generators must be among the other elements. And there are 8 other elements. And I use this isomorphism to compute the amount of generators. And I see that there must be 8 generators. So the blue elements are not the generators. So the generators are among the left, among the red ones. But there are exactly 8 red elements. So all of them must be generators because of the amount of elements. Is it clear now?
I didn't understand the connection between the number of generators and isomorphism.
Okay, so but model of that, is it clear? Okay,
yeah.
So I mean, if I explain how I computed the number of generators, then it will be clear to you.
I hope.
Okay, so let me explain how did I compute the amount of generators here. So you see, this group is isomorphic to this group. So these are exactly the same groups, but they are presented in a different form. Okay. So every element here, which is a generator, corresponds via this isomorphism. Well, if I find at least one isomorphism, but we know that there is at least one isomorphism. So every generator of this group here corresponds to a generator of this group here via this isomorphism. And vice versa, if I take a generator here, it goes to a generator here via this isomorphism. So if I count the amount of generators here, I will get the amount of generators here. So that's the key idea, that isomorphic groups are the same. They just presented in a different form.
Yeah, I understood that. But how did you count the number of generators in the Z16?
Okay. Okay. So as I already mentioned, that an element here is a generator. A here is a generator. So N is a generator. if and only if A is co-prime with 16. But what are the prime factors of the number 16? 16 is 2 to the power of 4. So being co-prime with 16 is the same thing as being co-prime with 2.
Okay, yeah, and then you just compare the number of generators in each groups. And I don't understand then why is generator if and only if it is co-prime to 16?
Okay. So, well, I didn't explain that fact, but okay, let's show this. So in general, this is a general claim, which means that if I take Zn star and I take an element, not Zn star, Zn, and I take an element A, so the element A generates the whole group if and only if A and N are co-prime. Well, okay. So first of all, suppose that so let's prove in this direction first. Well, suppose that A is not co-prime with N. So this simply means that, well, there is a common prime factor for N and A. So there is prime number which divides A and divides N, okay? And then it simply means that A belongs to a subgroup which is denoted like this. So it consists of all multiples of P. Well, here it must be something like N to the P minus 1 P. So these are, so this set, since N divides P, or since P divides N, these elements form a subgroup here, which is strictly smaller than the whole group. And since P divides A, element A belongs to the subgroup, so it cannot be a generator. So from this, it follows that A is not a generator. So we assume that this is wrong, and we have that this is wrong. So which proves left to right statement. So is it clear?
Yep.
Okay, so now let's show it in the opposite direction. So suppose that A and N are co-prime. So A and N are co-prime. Then we know that the element 1 is a generator of Zn. So we want to show that in this case, the cyclic subgroup generated by A is the whole group, but it is enough to prove that the element 1 is in the cyclic subgroup generated of A. It's enough, because if 1 is here, then every element generated by 1 is here, but every element generated by 1 is just every element of Zn. So, but now, in order to prove that, we will use this condition, and as usual, if we have this by an extended Euclidean algorithm, we have this equality. I already mentioned it, I didn't prove it, and I hope that you proved this during the discrete math course, but because of this equality, let's consider its modular n, then this summand is equal to 0, and we have 1 is equal u times A in Zn. So but what is here? Our operation is addition. So what is a cyclic subgroup generated by A? It's a subgroup of all elements, sorry, n is already used here. It's a set of all elements of this form. All the elements of this form. We just multiply a by all possible integers. And we see that we presented the element 1 in exactly this form, a times something integer. So this means that 1 is inside this subgroup, and this proves that in this case, the whole group belongs to the cyclic subgroup, so A is a generator.
Okay, that's clear. Thanks.
Mm-hmm. So that's how you do that. Okay, and let's try to compute generator. By the way, are there any other questions? I mean, regarding this computation. So in general, so you see, let me summarize what's going on here. So in this case, we took an arbitrary element, which was 2. And our first attempt gave us a generator. How did we get that it's a generator? Well, by using the fast rising to the power algorithm, we computed all the powers of 2. Well, actually, we did it by the brute force because we have to compute all the possible powers. We computed all the possible powers of 2. And after this computation, we see that's it. That's our generator. And we're done. In the second case, our first guess wasn't well enough. We didn't get the generator. We've got some subgroup, proper subgroup. But because we know this and some extra computation, we know how many generators we must have here. And it happens that all other elements that are not in our subgroup are automatically the generators. All the generators. That's what I mean. So, and in general, what you do, so you just pick an element from your group, start rising it to a power, and see if it's a generator or not. If it goes through all the elements, then that's it, that's your generator. If not, well, then you may use a trick like that, or if your tricks do not work, just take a different element, and with a high probability it will work. And if you want to have a good candidate for large numbers, element 5 is the one you should check first. Well, it's funny, but usually this is the element you're looking for. The second option is the element 3. For large prime numbers, just try to check these numbers 5, 3, etc. So these are the 2 ones you should check first. So here you don't have the element 5, but for large numbers you will have them. Okay, so now let's try to compute a generator for the group Z125 star, 125 star. So what is 125? It's 5 to the power of 3, yep. So it's just Z5 to the power of 3 star. And we know that it's isomorphic, since 5 is an odd prime number, it must be Z5 square 5 minus 1, which is 5 minus 1, 5 is 4. 4 times 5 is 20. 20 times 5 is 100. So it will be Z100. Let's try to find at least one generator here. And let me recall a general state. So an element here is a generator if and only if the 2 conditions holds. A must be a generator in Z5, so modular 5. And the second claim, the second condition, sorry, is a to the 5 minus 1 must be not 1 modular 5 square, which is 25. So we already described all the generators of Z5 star. We already described all the generators of Z5 star. They're here. We know that the generators here are 2 and 3. So the element, so the first condition here becomes A must be 2 or 3 modular 5. And the second condition is that A to the power of 4 is not 1 modular 25. So if we want to find all the generators of this group, we just go through all the numbers from 1 to 124, which are co-prime with 5, and check these conditions. But we can do it a bit more effectively. So since your number is equal to 2 modular 5, so suppose that A is equal to 2 modular 5, then you know that it looks like this: 2 plus 5 times k if you computed modular 25. And now, so you just check all possible numbers k here and check for the condition that it's not 1 modular 25. And that's how you list all the options for the element A. So, for example, let's try, let's try the element 2 itself. Well, if you take the element 2 itself, then A is equal to plus 5 times 0, modulo 25 is just 2, and it's not 1. So the element 2 is a good option here. And there are a lot of options here. So also you may take A to be 2 plus 5, which is 7. Then A modular 5 is 2, which is what you want. And 7 modular 25 is not 1. So it's not 1 modular 25. So it's also a valid option for your generator. And then you go in the same way. 2 plus 5 times 2, which is 12. And again, so this is not 1 modular 25. So this is also a generator, and so on. And you go through all the numbers such that A is not greater than 124, because you want to be in the group Z125 star. So you go through all these elements, and this is how you get all the generators with condition A is equal to 2 modulo 5. And then you have to repeat this procedure for the case A being free, and that's it. So here, let me just write it. So you consider exactly the same procedure when A equals 3 modulo 5. You just add 3 plus 2k, and you want it to be, you want it not to be 1 modulo 25. Again?
Why 2k?
Why 2 cases?
No, why 2k? 3 plus 2k. It should be 5k.
I'm sorry. Yeah. It should be 5k. It's just a silly mistake. Thank you very much.
May you please explain where you open brace, like we read like 2 conditions. So A is a generator in Z5 star, and like something like little Fermat's theorem. Where you get the second line from? Where
do I get the second line?
Yeah.
Well, that's a secret, actually. Well, I can explain your, well, actually the second condition means that element A is a generator in the group Z5 square star.
Yeah, well, yeah, it looks like so, but
yeah, but so, and it's actually well actually you may, well, if you have this condition, you just raise a to every possible power, and you see that you will get all the elements of this group. This is some annoying, unpleasant computation, which is like some classic for any number theory courses. But I don't want to spend our time for doing that. So let's try to do some more interesting thing, like let's try to encrypt and decrypt messages. So I just wanted to demonstrate how to use this claim, but I don't want to explain why it works.
okay.
But yeah, your intuition was right. This condition is the well, modular, the first one, means that the element A is a generator modular 25. And it can be proved that it's true. And by the way, in encryption, you could also use the group like that with a generator. So this method is useful if you want to find a generator for such a group. But usually people prefer using prime numbers here instead of powers of prime. And the reason is this: if this number is a prime, then Zp star contains p minus 1 element. So everything but 0 is in the group. But if it's a power of prime, like here, you decrease the amount of elements here by 25, as you can see. So it's p to the n minus p to the n minus 1. So you can still use this group in encryption decryption process, but here you have fewer elements than you could have if this number were prime. You see, so here you lost 25 elements. So in general, so people just do not like to use such group because you do not have a lot of elements here. You lost a lot of them. So that's the reason why people prefer to stick to prime numbers. Okay, let's try to encrypt something. We can actually play a game. So let our group G be Z5 star. We already computed everything that we need to know in order to communicate using this group. So we know that there are two generators, 2 and 3, and we can take any of them. So I want to take G to be 2, and we know that the other of the group is 4, okay? Mm-hmm. So let's so let me write down all the elements here, like 1, 2, 3, and 4. These are all possible elements. And I want to use a finite strings of 0 and 1. And I used this table to translate all messages to the elements of the group. So the table is really simple, is 1, 2, 3, 4. This is how I translate my strings to elements of this group, and I use the same table to translate them back. So let me give you a public key. So now here this is a communication like you, someone who wants to kill you, and someone who wants to communicate with you. Okay.
Why our spouse is supposed to want to kill us?
Because you have a lover.
You see, that's an interesting question. Sometimes it's not the spouse who wants to kill you. Sometimes he or she wants to join you. But in many cases, that's one of the most dangerous person in this communication process. So let's stick to our agenda, and we suppose that that's the spouse who wants to hack us with a shotgun. Okay. Okay. So, and now, well, our lover chose a secret key and this, or a public key, and the public key is free. We don't know the element B. So in this case, we know that the secret key is actually 2 to the power of B, where B is some remainder modular 4. So B here is a remainder modular 4. So just in case, so we have our group Z5 star, the generator G is 2 and the other is 4. So since Z5 star is isomorphic to Z4, so we choose an element B from this subgroup, and we raise the generator to the corresponding power, and this is our public key. So we know this public key. Everyone knows. Everyone knows it. And now we're so you want to compute your public key. Let's take so we know how to compute our public key. We should take some element A, and let's take it to be 2, which is an element from Z4, and we want to compute our public key. Could you tell me what the public key is?
4.
Yeah, the public key is 4. And we transfer it to everyone. Now, could you compute the secret key? By the way, is it clear to everyone why the public key is 4? Are there any questions at this moment?
Not really. Why is it 4?
Why is it 4? Okay, so how do you compute your public key? Your public key is computed with this process. You take the generator G and you raise it to the power A, the one you have chosen. So here it's 2 to the power of 2, which is 4.
Oh, okay.
And just in case, your public and private keys are the elements of the group. So they are not numbers, they are elements of your group. So the red thing here and here, they are numbers from Z4, but these could be any group. Z5 star is just an example in this case. So now, is it clear to everyone what's going on here, or are there any questions regarding this situation? Okay, so now we have this public key and the public key of our lover, and we want to produce the secret key. Could you produce the secret key? So I'm specifically, well, I want to hide this B in order to show that you can compute everything without this knowledge. You don't need to know this number B. So could you compute the secret key?
Is it 4 to the power
4?
B?
It's 4 because it's 2 by 2.
Again?
It should be 4 because it's our A multiplied by 2 because it's our generator, yeah?
Well,
I'm a bit confused right now.
so so how, so at the end, we must get G to the power AB, but we don't know B.
Okay.
Because you see, we don't know. We know only S, but what is S?
It's G to the power B.
It's G to the power of B. So how do you get G to the power of AB if you know G to the power of B?
Raise it to the power of A.
Yep, so our private key is S to the power of A. So we take the private key or the public key of other participant and raise it to the secret number A we have chosen. So in our case, K must be free to the power of 2, which is what?
1.
1. Oh, 9. Wait,
9 modular 5.
5 is 4.
It's 4 now.
It's 4. The same thing as minus 1. Okay, so our private key is 4. Okay, now we are ready to communicate. We know a secret key. So our lover says he knows or she knows the number B. She or he can also compute the private key. So she or he knows how to encrypt the messages. And now she or he sends us a message. So let me show you the message. We were getting a sequence 2, 3, 2, 1. This is an encrypted sequence of elements of the group M1, M2, M3, and M4. I want you to decrypt this message. Could you decrypt M1 and get H1? Do you remember how to decrypt? Could you write me the formula?
Oops.
H
Okay.
is M1 multiplied by K, and then we need to know the inverse to decrypt.
Yeah, Oleg is right. We should multiply by the inverse of the key, because how do you decrypt this? We know that before sending the message, our lover multiplied all these elements by K, by the secret key, H1K, H2K, H3K, and H4K. And these are your elements M1, M2, M3, and M4. So M1 is H1 times K. So if we want to recover the element H1, we must multiply by K inverse. So this will be M1 times K inverse. So now I want you to compute this.
So H1 is 3, I suppose.
Yep, it's 3. Now, just in case, is it clear to everyone how we get this H1 here? Should I explain it? Should I repeat something or anything? Okay, good. Now, tell me the answers for all the other elements.
2, 3, and 4.
Good. Now, could you recover the original message?
Okay, we need. So it's.
The table is here.
So it's 1 0 0 1 1 0 1 1.
Yep. You see how creative our lover is. That's a pretty nice message. The lover is very kind, and the message is very pleasant. So that's how the whole process goes. Now,
Can you encrypt photos with this method?
what again?
Can you encrypt photos with this method?
Photo is just a collection.
Oh, okay.
Of
Let's me encrypt 4 with this method. So for example, we have like M5, which is 4. Okay. So then H5 will be M5 times K inverse. Okay. Then what is M5? M5 is 4, and k is also 4, so we multiply by 4 inverse, and we will get 1. Let me see. Sorry, 1. So this. Oh, that was decryption. You asked me to decrypt 4. Am I right?
Yeah.
Okay, so I'm sorry. So that was decryption. So how to decrypt 4? But let me show you how to decrypt 4. So in order to decrypt 4, so suppose now you have like H4 is 4, yeah, and we want to decrypt. We want to produce M4, which is H4 times K. And this is what? It's also 4 times 4, which is 1. And this is your M4. And if you look at the message sequence, the last message was 1, exactly. So is it clear now?
Yeah, thanks.
Okay, so actually, you could do you could do this. Well, in general, with any possible group here. So, but instead of 5, you should take like some very large number, and well, you will get something like Z29 star in the homework. So it's enough to encode all the English letters and also 2 additional symbols, and you will try to decrypt a message from your lover. So also we could play some game and try to communicate via the chat right now, or we could discuss one more example. I don't know, what would you prefer?
Game.
Game. Who wants a game? Just write plus into the chat. Okay, I see. Okay. I need 2 volunteers. So, okay.
It's me. Take me.
Okay. Since I can't recognize you by the voice, just write down.
Anton Ivanov and Alexander Yegorov.
Okay, Anton and Alexander. So let me show this. So let me play this game. So here's me. Here is chat. And here is Anton. And here is Alexei. Am I right?
Alexander.
Yeah.
Alexander. Alex. Okay, now we will use the same group, Z5 star. The generator there will be 2, and the amount of elements is 4. I'm telling you my private key, which is again free. So I just don't want to recompute everything. So let's my public key to be exactly the same as before. It's free. So everyone knows my public key. So now I want to ask you, Anton and Alexander, to choose some number A from Z4. Please generate your public keys.
Okay, so mine will be 4.
Who was that, Anton?
It's Anton. Yeah.
Your public key is 4. Now, Alexander.
I shall take an
Just
element
don't tell
from
us your secret number 8.
Yeah, I understand. And raise it to power of 2.
You should you should take the generator G, which is 2, and raise it to the power
Raise it
of
to the power
8.
of 8.
Yeah, that's your secret.
Let me think. Okay, I've chosen my number and I raise 2 to its power and modulo 5, yeah?
Yep, modulo 5.
Okay, then my public key is 3.
Okay, your public key is 3. So now I want to send you a message. Well, I will send a message to Anton and to Alex, and I want the chat to brute force and to try to encrypt the message I'm sending, okay? So just give me a second. I will write down the message. This is for Anton. The message is, so his public key is 4. So for this public key, I will use 432. This is a message for Anton. Anton, I want you to decipher, to decrypt my message,
Okay.
but do not tell anyone the answer.
Okay.
So, Alex, my message to you is this: 241. Please decrypt my message using your my public key and all the information you have. And everybody else, please try to find the secret elements that I generated for Anton or for Alex. Just
should we tell you what we come up with? Like,
when you are ready, please tell me that you are ready.
Okay, I'm ready, I suppose.
So, Anton, you already know the...
I think I'm not going to come up with anything because I don't understand how to do it. How do I have to count a secret key now.
Yeah, you need to count the secret key.
Which is K, which is generated to the power of AB.
So how do you count the secret key? Let me recall you. You take my, so you know that my...
private key and raise it to my power.
Yeah, you take my public key and raise it to your power. So this was G to the B, where B was secret. That was secret B.
Okay.
So,
and modulo 5.
Yeah, everything is done modulo 5 here. So, and don't tell anyone the secret key. So Anton is ready. Yep.
Probably.
Okay,
if I'm not mistaken.
So if anyone in the chat knows...
Oh, our messages are quite interesting,
Yeah.
And what do you do with K then? With n to the power of -1?
But now this secret key was used to encrypt my original message, H1, H2, H3. So that was original message, and this is what I have sent to you. So the element 2, how did I get the element 2? I multiplied H1 by the secret key, and then the result was 2. So in order to recover the original message, you must multiply the element 2 by the key inverse, the K inverse, where K is your secret key. So this is how to decrypt every element. Is it clear?
Yes. But,
so try to decrypt all of them, but do not tell anyone the answer. But is there anyone in the chat who knows how to decipher this without knowing all the secret information? Because you don't know B and A1 or A2. And Alex, just tell me when you're ready, when you know all the...
Yeah, one sec, just one sec.
No problem, no problem. Okay. People in the chat.
Okay, I hope that I deciphered it.
Okay, so now, is there anyone in the chat who knows how to decrypt at least one symbol here and get the original message? Is there anyone who knows how to do that? Okay, so you see, Anton and Alex already know the answer. They know what kind of message I have sent to them, but no one else knows the original message. Now, Anton, please tell me.
But should this message be the same?
Yes, our message is the same.
Your message is not the same.
Okay.
Our message is 1, 2, 3.
Yep, it was 1, 2, 3.
Cool. I've got 3, 1, 4. Okay.
Aha. So
Are you sure that you took a module of 5, not module of 4 plus 1?
Okay.
I don't know.
I've chosen my A as 3.
Yes, your
2
A
to the power
is 3.
3 is 8. 8 modulo 5 is 3. So my
3.
my
And then you need to take your inverse. It's 2.
But now, what was your secret key?
My secret key was 3. So my public key is also 3.
Yes, but then your secret key was also, you need to take inverse of your secret key when you decrypt.
And what is K then? K is 4, isn't it?
Well, probably just 1 second. 2, 4, no. So your secret key must be 2.
Well, yes. So secret key or inverse of secret key, I don't know.
So the inverse of the secret key is what?
No, why is it 2? It should be 4. It is 3 to the power 3 modulo 5.
And it's 2.
Ah.
You made a mistake.
So wait. 3 to the power 3 is 27. It's yeah. It's
Okay,
2. Okay, K is 2. Then K to the power 3 is 8. 8 and
well, I would suggest.
Yeah.
So let me suggest a better computation. So now you want to. Let me clarify. So your secret number was 3. Yep.
Mm-hmm.
So and now you want to compute 3 to the power of 3 modular 5. How would you do that? How would I do that? So first, I would say that this is 9 times 3. So I just rise to the power of 2, and then left 1 3 here. But now I just simply, before multiplying next, I simplify 9. So 9 modular 5 is what? Is 4. Okay.
Okay.
And now, when you multiply 4 by 3, it's 12, and modular 5, it's 2. This is how to speed up your computation. Okay, is it clear? So, okay, so as you can see, so I just demonstrated to you that we can communicate without knowing these numbers A1 and A2. These are the secret numbers you don't have to tell me, and neither I have to tell you my secret number B. And actually, as you can see, since we have the same public keys, we have chosen exactly the same secret number. So my B was actually 3. Yeah. And and now we can communicate. I send you a message, and actually you can also encrypt a message and send it to me, and I can easily decrypt it using exactly the same procedure. And no one else can recover the original messages. The only way to recover this is to find A and B solving discrete logarithm problem using these numbers and this generator. So in order to decipher this, you just use the brute force. You just seek for the secret A and B, well, for the A1 and B in case when we communicate with Anton, and for A2 and B in case when we communicate with Alex. So for each participant, you have to solve this discrete logarithm problem. So if there are two participants, then you have to solve it twice. And if I change the key each time I send a message, then you have to solve this problem again and again for each piece of the message. So I hope it's clear that it's not feasible if the number here is large. Well, now it's like a toy example where 5 is a small prime number, but well, it's a good teaching example because you have to see how it works with small numbers. But if you want to use it, you just choose a prime number which contains like 100 digits. And then there is an algorithm to produce such a large number, like there is a good algorithm to produce very large prime numbers. And then you just use this prime number. And no one is able to decipher whatever you encrypted. So that's how it works. So I hope it was clear. So we have like 4 minutes left. So if you have any questions regarding what's going on here, then please ask. Yeah, so this homework I hope will be more interesting. So you'll have to decipher a message in English. It won't be a string like that. So you will know exactly what your lover is going to tell you. I hope you will be glad to receive such a message. So if you succeed, you will get a message containing an English phrase. So, and if it doesn't make sense, then you will see that the decryption stage failed somehow. And if you will get a readable phrase, that will be the best confirmation that you did everything right.
Okay.
Okay, if you have any, if there is no questions, then thank you for being here with me. I hope it was interesting. I hope it was useful. And
I have a very stupid question, actually.
Okay, no problem.
Regarding the previous lecture and seminar. So
okay.
If we have a group like ZP and group ZQ, so these are additive groups, and P and Q are some primes, and we want to, from these multiplication of groups, construct the isomorphism to ZPQ.
Just give me a second. I will write down what you're asking, just in order to. Oh, you're writing this. So yeah. ZP, okay, and we want to write this. Yep.
Yeah. So well, I'm not sure, but I think that if we have like a function phi of xy, there when x is like an element of ZP and y is element of ZQ, if it maps to something like so Q multiplied by X modulo P. What am I doing? No. Yeah, I forgot. What I just want you to remind what would be the algorithm to make it, because
oh, you forgot the way how to produce the inverse map here.
Kind of, yeah.
Okay, could you erase this?
Yes, I'm doing it.
Okay, and I'll recall you the algorithm. So what do we have here? So in general, we have Z. So, but I prefer to write in the opposite way. It's easier for me to think when everything is written from left to right. So, and we're going to produce the map in the other direction. So first of all, I want to produce. I want to find an element x and y with this property. X corresponds to element 1, 0, and y corresponds to the element 0, 1. That's the first thing I want to do. And I do it using this thing. Since P and Q are coprime, I can present one as a sum U times P plus V times Q. Okay? And then the elements, then X will be VQ and Y will be UP. So that's the first step. And on the second step, if I want to send an element AB to something, I send it to A times X plus B times Y. So, and this is the map in the opposite direction. So this is how you predict it. So you find these elements and then you write the map in the opposite direction using this.
Then I have another question.
Yeah.
So if we have...
But we're running out of time, so that's the last question, okay?
Yes, that's sure. So if we have like, okay, ZP times ZQ, and we want to construct an isomorphism into ZP with this thingy and ZQ, and we know that there is such an isomorphism, because, well, from some transformations. So is it okay if we construct an isomorphism to some like intermediate group? And then from this
that's how it should be done.
Okay.
That's exactly how it should be done.
Okay, so like isomorphism of isomorphisms is like isomorphism. Like, so it's like a transitive property.
Yeah, composition of isomorphisms is an isomorphism. I didn't mention that, but I hope it's clear.
Okay. Then no questions.
Okay, thank you guys. Then that's it.
Will you share this slides with us?
Yeah, I will share everything.
Thank you.
I'm sorry, and what about the videos? We do not have the videos, like exact video, not only the seminar, but...
Okay, I wrote a message to Naira, and she told me that she will upload everything to the YouTube channel, which is called in Russian FKN, удаленное образование.
Okay. So I just didn't know that we have a channel and its name particularly. So, okay, thank you very much. And for the lecture.
So she must write an email to all of us when everything will be uploaded. I don't know why it's taking so much time, but it must be uploaded soon. I will remind her today, and if there are any videos there, then I'll send you an email with the information. Okay, then thank you guys.
Okay, thank you. Goodbye.